going to be talking about how to convert between grams, moles, and number of particles. So for this, you're going to need a periodic table, and you'll need your calculator. So grams, that's mass. Moles is a way of measuring the number of particles. It's just a very useful unit. I mean, if I said how many moles of flour, how many particles of flour do I have here? Literally, how many little tiny molecules? The number would be so ridiculously large, it's not very practical. So we use moles as a way of kind of simplifying that. You know, it's sort of like a dozen of something is 12. Well, a mole of something is just going to be 6.022 times 10 to the 23rd. And number of particles, this can kind of have a few different meanings. For certain things, that's going to be the number of atoms. Because basically certain substances are individual atoms, like a piece of steel, like this. This is made up of just individual iron atoms. Okay, steel's not the best example. Assume this were actually iron. This would be, just a bunch of iron atoms. So when I say number of particles, I mean how many atoms. Something else like a sample of water, I wouldn't really ask how many atoms of water there are, because water is not an element. For this, I would say how many molecules of water. So molecules are going to be like the distinct, kind of separate bonded units that make up a compound. And the last term that we should know, and I'll write all these down. So number of particles, that can either be atoms, that could be molecules, and that could be something called formula units as well. Now, what a formula unit describes is the simplest unit of a repeating ionic compound. So basically, when we have water, you have H2O, right? So you have H, O, it's done, it moves on. So it's literally just three atoms bonded together and then it goes. But when you have something like NaCl, when you have a sample of salt, when you have a sample of salt, it's not NaCl bonded together and then go. It's not like you have separate NaCl molecules like this. Okay? What you have in NaCl is a repeating pattern of NaCl, 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 three-dimensional. It's a repeating pattern, so it doesn't really make sense to talk about a molecule of NaCl. A molecule of water makes sense because that's distinct, but NaCl doesn't really make sense. And I kind of Googled an image here. Like, this is what an NaCl would look like. Now, that's not one individual cube because these are atoms. This would be much too small, but it's this repeating pattern. Okay, so you can either use atom, molecule, or formula unit for that. Okay. Well, let's go through an example here just to start out and see how we do this. So number one, how many moles are in 953 grams of aluminum? So, I have some aluminum foil. Let's say that the foil in here has a mass of 953 grams. I want to find out how many moles that is. Well, we have to use Avogadro's number. Okay? So this you should write down, have memorized. Avogadro's number, 6.022 times 10 to the 23rd. Now what Avogadro's number means is the number of particles in a mole of something. It would be sort of like how a dozen is 12. So a dozen of something is 12 of that. Well, a mole is Avogadro's number of something. So if I say how many moles are in this many grams, basically what I want to find out is how many times I have this many aluminum atoms. Okay? So the way we figure this out is you look at your periodic table and you look at the number underneath the aluminum. Okay? Now the number above it, that's 13. That's the atomic number of protons. We're looking at the number underneath, the decimal. So it says 26.982. That's known as the molar mass. That's the mass of 1 mole of aluminum atoms. Okay, so what you want to write down is 1 mole of aluminum equals 26.982 grams. 26.982 grams. Okay? So when I say how many moles are in 953 grams, we're going to set up a conversion factor. So we're going to be converting grams to moles. So I start by writing what I'm given, 953 grams. And now I'm going to turn this into a fraction. Well, 1 mole equals this many grams, and really this is specific for aluminum. Okay? So I want grams to turn to moles, so I'm going to put my 1 mole over 26.982 grams. Gram cancels gram. Let's see what we get. 953 divided by 26.982 equals 35.359157. We want to look at sig figs, 3 sig figs here, so I'm going to call it 35.6. And my unit is moles. Okay? You can write MOLES or just MOL. So, how many moles are in this many grams? 35.6 moles. Okay? Number 2, what's the mass of 0.85 moles of iron? Well, we need to look at iron on the periodic table. This might take some time initially, but before too long, you're going to pretty much have most of the common elements memorized where they are. So iron is Fe, number 26. So for iron, 1 mole of Fe equals 55.847 grams. Of Fe. So for this problem, we're going to start with 0.85 moles. We want to turn this into grams, so I'm going to put my grams on top of my moles. 55.847 grams per mole. Mole cancels mole. So we multiply these together. 0.85 times 55.847. And that gets me, with now 2 sig figs, I'm going to say 47. 47 grams. Okay? Now let me stop here real quick. The number underneath the element, you may know that as the atomic mass from like biophysical science, which is how much the atom actually weighs. Now that's true. It is how much the atom weighs, but that's in a special unit called the atomic mass unit. So the atomic mass unit weight is the same thing as the molar mass in grams, and that's what we're going to be using it for molar mass. Okay? So let's move on. Number 3, how many atoms are in this sample of iron? Okay? So now we're actually taking it into number of atoms. So grams to moles is very simple. You just use a periodic table, go back and forth between grams and moles using that molar mass. For number of atoms, we need to use Avogadro's number. So let's look at how many we were dealing with. So we had 0.85 moles. And we also figured out that it was 47 grams. Okay, so that's how much iron we had. We're saying how many atoms are in this sample. Now what you're going to realize is when we want to convert into number of atoms or number of molecules or number of formula units, you're not going to use the mass. You're going to use the moles. And we're going to use the moles with Avogadro's number. So 1 mole equals 6.022 times 10 to the 23rd particles, as we normally say, but in this case, it's going to be atoms, because 1 mole of iron is going to be this many atoms. Okay, so Avogadro's number with the mole. We're not going to use grams at all. So how many atoms are in this sample? Well, we start with 0.85 moles times, now we want to turn our moles into atoms, so we're going to say 6.022 times 10 to the 23rd atoms per mole. Mole cancels mole. Multiply these together and let's see what we get. Now you got to be careful multiplying these. I mean, you can do it out kind of by hand like we did earlier on in the year, but you know that's not necessary. So in my calculator, I'm going to put this number first, times 10 to the 23rd, and I'm just going to let my calculator store that. So I'm going to say 6.022. I use the E, but you don't have to. You could just say times 10 caret 23, and I just say equals. And I just let my calculator store that number just as it is. And now I'm going to say times 0.85 equals, and here's my answer, 5.1187 E23. That E means times 10 to the. So with 2 sig figs here, I'm going to say 5.1 times 10 to the 23rd. And my unit is atoms. Okay, so if you have a 47-gram sample of iron, a little tiny piece of iron, that's how many atoms you have. 5.1 times 10 to the 23rd, which is really like a 5 followed by 23 zeros. What is the mass of 6.31 times 10 to the 25th silicon atoms? Okay, well, we're given the number of atoms and we need to find the mass. So basically the pathway is going to look like this. You can have mass, or let's put it as grams. Grams, moles, and number of particles. Okay? You can either go from grams to moles to number of particles or the other way, but moles is always going to be like the middleman. You can't go from grams directly to number of particles. You can't go from number of particles directly to grams. Moles is going to be the middleman, so we're going to be going, in this case, from the number of atoms to moles, and then from moles to grams. It's going to be like a two-step problem. All right, so first we need to look up the molar mass of silicon. So that's going to be number 14, silicon. So we're going to say 1 mole of Si, silicon, equals 28.086 grams. Okay, and we also know Avogadro's number, so 1 mole equals 6.022 times 10 to the 23rd atoms. Okay, so we're ready to start. We write our starting point, 6.31 times 10 to the 25th atoms. So we need to turn this into moles, and then we'll turn that into grams. So to turn this into moles, we use Avogadro's number times 1 mole per 6.022 times 10 to the 23rd atoms. Atoms cancels atoms. We're left with moles. And let's take this directly into grams. No need to do the math and then do the math again. So this is going to give us moles, and now we're going to turn it into grams. So I'm going to put my grams on top, 28.086 grams per mole. Mole cancels mole. We're left with grams, and let's see what we get. So at this point, notice, we're multiplying by a number in scientific notation and dividing by a number in scientific notation. It's very important that you put this in parentheses here, because if you say 6.31 times 10 to the 25th divided by 6.022 times 10 to the 23rd with no parentheses, your calculator thinks in terms of PEMDAS, in order of operations. And it's going to go this times this divided by this, but then times that. So you want that in parentheses. So the way I would set this up, I'm going to put this number in my calculator first, 6.31 times 10 to the 25th equals, I just let my calculator store that value. Now I'm going to say divided by open parentheses 6.022. I use E, so E23, or you could just say times 10 to the 23rd, close parentheses. Make sure you close the parentheses there, and that'll get you the number we're looking for. And it's good to stop and look at this number. So it said 104. Does that make sense? Well, the 6 divided by the 6, pretty much 1, right? And when you divide numbers in scientific notation, you subtract the exponents. So 25 minus 23, that's 2, so 10 to the second. So it should be about 1 times 10 to the second. Makes sense. If you do this and you end up with a number like 48, 10 to the 48th, you messed your parentheses up. So we got that times 28.086, 2942.92. Let's check our sig figs. 3 sig figs. So I'm going to call this 2940. And the unit is grams. Okay. Number 5, how many moles are in 60.3 grams of NaCl? So we've added one kind of level of complexity here. Instead of just a regular element, now I'm giving you a compound, NaCl compound. So we're going to need the molar mass of that compound. And it's literally as simple as finding the Na mass, finding the Cl mass, adding them together. Okay? So So if you look on your periodic table, Na is number 11, sodium, so that's 22.990. There's one sodium atom, there's one chlorine atom, so we just add the chlorine. So chlorine is 35.453 equals 58.443. So 1 mole equals 58.443 grams. Okay? Well, I'm giving grams, I want moles, very simple. 60.3 grams times 1 mole over 58.443 grams. Cancel grams, cancel grams. So we just go 60.3 divided by 58.443 equals, and with 3 sig figs, 1.03 moles. Moles, M-O-L-E-S, or M-O-L is fine. Okay. Number 6. How many water molecules are in 100 grams of water? Okay, so notice I'm not saying water atoms because water is not an element, so it's going to be water molecules. Well, for this, we're going to need 2 things. First, let's say 1 mole equals 6.022 times 10 to the 23rd, and remember that's number of particles. But in this case, we're not looking at atoms, we're looking at molecules. So it's going to be 1 mole equals 6.022 times 10 to the 23rd molecules. Okay. We're also going to need moles. Okay, because remember, we can't just go from grams to number of particles. We have to use moles as like the middleman. So for H2O, we need to go add up 2 H's and 1 O. Okay, 2 H's and 1 O. So hydrogen is 1.008 times 2. Make sure you get both hydrogen atoms, times 2, plus oxygen, which is 15.999. And this works out to be, so we have 1 mole equals 18.015 grams. Okay? We're ready to start the problem now. So we're starting with 100 grams of water. We need to take this into moles. Moles is the middleman. So times 1 mole over 18.015 grams. Gram cancels gram, that gets us moles. Now that we're in moles, we can see how many molecules of water that is. So, times 6.022 times 10 to the 23rd molecules per mole. Mole cancels mole. Let's see what we get. So 100 divided by 18.015 equals times, and I'm going to do an open parentheses here. I guess it really doesn't matter because it's this times that. It's not going to mess up the order, but I always use parentheses. Times, open parentheses, 6.022 times 10 to the 23rd close parentheses equals, and with 3 sig figs, 3.34 times 10 to the 24th. And my unit is molecules. Molecules. Okay? And don't forget, like your calculator is going to say this. Don't just write 3.34. You see the E24 there, that means it's times 10 to the 24th. Okay? It does not make sense that there's 334 water molecules in a regular size beaker like this one. This is a 100 milliliter beaker. If you fill that with water, you got 3.34 times 10 to the 24th water molecules. All right. How many moles are in 16.3 grams of Ba3 parentheses PO4 close parentheses 2? Now, within about a month, you're going to be able to name that, barium phosphate. But for now, it's just going to be kind of a formula. And again, you'll see it written like this. Ba with a subscript 3, open parentheses PO4 close parentheses 2. Now, you got to make sure you know how many atoms are in this formula. Okay? So for barium, we have 3. It's simple, barium 3. But then the parentheses has a 2 outside of it. So it's sort of like in math. When there's a 2 outside the parentheses, you distribute that 2 into it. What this means is that you have 3 barium atoms, 2 phosphorus atoms, and 8 oxygens. Notice we have O4, but it's 2 of them. So we're looking for the number of moles in this many grams, so we just need the molar mass, but we're going to need the molar mass of this entire thing. So you look up barium, which is number 56, so it's 137.327, okay, that's on your periodic table, times 3, okay? So I just let the calculator hold that. So that's my barium. Now we're going to add the phosphorus, okay? So I'm going to say plus, phosphorus is 30.974, times 2, okay? Now, you got to make sure you're careful with the order of operations here. This is fine, okay? You wouldn't want to say plus 30.974 equals then times 2. Okay, you can also just kind of work this out by hand, however is easier for you. Okay, so you add that, now we're up to this, and now we just have to add our oxygens. So we have 8 oxygens, so I'm going to say plus 15.999 times 8 equals, and that's going to be your molar mass. Okay, 601.921. So 1 mole equals 601.921 grams. And now we solve the problem. So I'm given 16.3 grams times 1 mole over 601.921 grams. Cancel, cancel. 16.3 divided by this number gives me 0.0270799 and so on. 3 sig figs. I'm going to say 0.0, and remember that 0 does not count, 271. And my unit, moles. Okay. So 3 more for you guys to work on. I would say pause the video, try to work these out, and then resume it and I'll solve them. So go ahead and pause. Alright. Number 8. How many oxygen gas molecules, O2, are in a 50 kilogram tank? Assume the tank is 10 kilograms. The tank. Assume the mass of the tank is 10 point kilograms, so the gas is 40 point kilograms. Okay? So basically we're saying how many gas molecules are in 40 kilograms of oxygen gas. Well, we're going to need the, so now we're going from grams to number of molecules, so we're going to have to use the middleman of moles. And to do that, we need the molar mass. So on the periodic table, oxygen is 15.999, but I'm not just talking about oxygen atoms, I'm talking about oxygen gas molecules, which is O2. So we're going to say 15.999 times 2. So 1 mole equals 31.998 grams, okay? Because it's O2, it's not O. But notice I give kilograms, we're going to have to convert that to grams, okay? So very simple, 40 kilograms, that's 40,000 grams. With 2 sig figs. No need to take the time to write that out. We'll do sig figs at the end. All right, so let's start the problem. 40 point kilograms, but it's got to be 40,000 grams. Okay, let's convert to moles. Times 1 mole per 31.998 grams. Cancel, cancel. That gets us moles. In other words, moles, we do number of particles. So that's going to be Avogadro's number times 6.022 times 10 to the 23rd molecules per mole. Mole cancels mole. So we do the math. 40,000 divided by 31.998. Oops. 40,000 divided by 31.998. Times, and I'm going to use parentheses here, open parentheses, 6.022 times 10 to the 23rd, close parentheses, and with 2 sig figs, I'm going to say 7.5 times 10 to the 26th, and the unit is molecules. Molecules. 7.5 times 10 to the 26 molecules. Okay. Number 9, what's the mass of 1 cobalt atom? 1 cobalt atom, so it's going to be very small. Well, let's see how we're going to address this one. We need to know how many, basically, mass to number of particles, we're going to need to use the middleman of moles. So I'm given one atom, so I'm going to take the one atom, see how many moles I have. It's going to be like an astronomically tiny number of moles. And then I'm going to take the moles and go into grams. So let's look up cobalt here. Cobalt is number 27, 58.9332. So 1 mole equals 58.9332 grams. All right, so we have to start by taking our atom and put that into moles. So 1 atom times, and we're going to use Avogadro's number here, times 1 mole per 6.022 times 10 to the 23rd atoms. Cancel, cancel. Obviously, this is going to be a ridiculously small number, but we'll move on. Now that I have in moles, I'm going to use this to get to grams, times 58.9332 grams per mole. Mole cancels mole. This should get us our answer. So 1 times 1, you could just say 1, divided by, open parentheses, 6.022 times 10 to the 23rd, close parentheses. Okay, make sure you get this number so you don't forget your parentheses. And that makes sense because I have, you're dividing by 10 to the 23rd, you should get a very small number. And I'm going to take this and multiply it by 58.9332. And with, well, how many sig figs? Well, just one. If I have one atom, it's 1 sig fig. So, a little tricky. Okay, so the answer is 9.786 times 10 to the negative 23rd. So I'm going to have to make that, this isn't that bad. I'm just going to make it 10. So the 9 is going to turn into a 10. So it's 10 times 10 to the negative 23rd, and the unit is grams. But really, that's not proper scientific notation. So I'm going to make this smaller. This has to be a 1. So that has to be bigger. So the 10 is going to go down to a 1. Let me write it in black here. 1 times 10 to, and this as I went down, this goes up. So negative 23 is going to go up to negative 22. Okay, and that is grams. Okay, and really what this looks like is 0.21 zeros and then a 1. So it's like a very small number of grams. Okay, last problem. How many moles of CO2 are in 39.2 grams of dry ice, solid CO2? So this one's real simple. CO2, we're going to find the molar mass. So carbon is 12.01. Well, 12.011. That's 1 carbon. Now we're going to add 2 oxygens. So I'm going to say plus 2 times 15.999. So CO2 is 44.009. So 1 mole equals 44.009 grams. Okay, so now it's as simple as going like this. 39.2 grams times 1 mole over 44.009 grams. 39.2 divided by 44.009, and that equals 0. Let's check our sig figs. 3 sig figs, so I'm going to say 891. And my unit, moles. Okay, so that's basically it.